Just to warm up, I want to do an integral. So this is just going to be the integral of dr over r squared from a to b. Okay, so let's go ahead and settle down. So this is going to be doing this integral right here. We've seen integrals of this type quite a bit. And when I evaluate this integral, what I end up getting is this is 1 over b minus a. Right? Anybody agree? Anybody disagree? Yeah. Yeah. What do you think?
Isn't it a minus b with a negative?
Well, that could be part of a problem here, but that's not the primary problem. So you're saying, okay, there should be a negative sign here. Yeah, that is an issue. There's another issue here. Yeah. Exactly. So really what this is minus 1 over r evaluated from a to b, which is equal to minus 1 over b minus 1 over a, which is not the same thing as minus 1 over b minus a. Okay. So important point, and you'll find, and I'm guilty of this too, the more calculus that you do, the faster you get at it, and then you say, okay, well there's some shortcuts that I can take so I don't have to write out every step explicitly, but you have to make sure that if you do take shortcuts that you don't make mistakes. And this was actually a very common mistake that I saw when I was grading the homework, that when people did this integral they jumped over to here, but it's actually not true. Okay, and you could see exactly why that is if you wanted to plug some numbers in here. Say b is 5 and a is 2. Well, 1 over 5 minus 1 over 2 is not equal to 1 over 3, right? Or it's not equal. This is going on the internet. I don't want to make mistakes like that. Okay, so to get into the real material for today, let's talk about circuit analysis, starting first with the rules for circuit analysis, and then I'll do this example. So the first thing that we want to do is we want to write down the two critical equations for circuit analysis. So if you took physics in high school, or probably if you took this from somebody other than me, you'd be using Kirchhoff's rules for circuit analysis. Who's seen those before? Yeah, quite a few people. I don't use Kirchhoff's rules because they unnecessarily introduce some negative signs, and they're also not exactly consistent with some of the things that we're going to do later. So for the sake of consistency, I do things in a slightly different way. And that's to say that the two important equations that I have are the integral of E dot dl is equal to 0. So this is just some statement about the electric field being a conservative field. And the second equation is the integral of j dot ds in general is equal to minus dq dt, which in a special case, when the charge is constant, is equal to 0. Okay, so let's talk about what these equations mean. First, the first one we can think about by going back to some of the things that we learned last semester when it came to conservative forces. So consider some path like this that I can go around. If this is the x direction, this is the y direction. And as I move along this path, the only force that I'm going to experience here is the force of gravity. Okay, so let's say that there's some force F is equal to minus mg y hat. And what we want to do is we want to show that for this particular force, if I go around this closed path, the integral of F dot dl is equal to 0. Okay. So in order to do this, what we need to consider is the fact that there are 4 elements to this path. So the integral over the closed path is just going to be equal to the sum of the integrals around the path. And so that says that there are 2 parts in x. So there's going to be an integral, let's say that this is a point AB. This is going to be the integral for this portion. This goes from 0 to a in x, so 0 to a of f, let's say this is f g dot x hat dx, plus the integral from 0 to b of f g dot y hat dy, plus the integral from a to 0 of f g dot x hat dx, plus the integral from b to 0. So this is the integral from b to 0 of f g dot y hat dy. Okay. Now what we see here first is that because our force is only in the y direction, the dot products with x are going to be 0. So this is identically 0, and so is this one. And then these ones are going to have dot products that are not 0. And what ends up happening here, because this is a conservative force and it's actually just constant in y, when I look at these integrals, they're going to cancel each other, which says ultimately that the integral around the closed loop here for the force of gravity is equal to 0, and that's really what I'm getting at. So going back to the things that we talked about last semester, we talked about this in terms of for a conservative force, the work around some closed path is equal to 0. I'm using that same idea here, only with an electric field. So I say, if I sum up all of the contributions of the electric field around some closed path, if that electric field is conservative, it's equal to 0. And that's going to be identically the case for our time-independent circuits. The second equation that I have here is what's called the current continuity equation. And what this says is, what does this left-hand side look like? Looks very much like something we saw before, only with a slightly different symbol. What does it look like? I have an integral over a closed surface, something dot ds. It's a flux calculation. What integral over a closed surface for a flux did we use previously? Say again? E field? Yeah, the electric field, and that was Gauss's law, right? So in interpreting what this equation means, it's the same exact idea. So when I was talking about Gauss's law, I had some electric field that was going out of some closed surface. I added all that up, and that said that it was equal to the charge in divided by epsilon naught. Here, that's the right-hand side is slightly different. The left-hand side is only different via the J versus E. And what this says is, add up all of the current density that flows out of some closed surface. That's going to tell you something about how the charge inside that surface is changing with respect to time. And so you can think about current density as current moving or charge moving. And if charge is moving out of a surface, then that's going to be some decrease in the charge contained in the surface. Now, in a special case where you say that the charge inside is going to be constant, you can say that the flux out of this closed surface is going to be 0. And so this is akin to saying whatever I have going into the surface is what I have going out of the surface. And so what this ends up reducing to is the junction rule that you've seen before probably, that says that the sum of the current in is equal to the sum of the current out. So just to get this on the level of the things that you've seen before, this is kind of like Kirchhoff's junction rule, and this is kind of like Kirchhoff's loop rule. The difference really is here. There's a negative sign. That you don't have in this case. Okay, so getting to the rules for how do you apply these two equations, I'm not going to write them down, it's a little bit lengthy, but first thing that you want to do for any circuit that you have is to label the direction of the currents and the charges. Now these are kind of arbitrary things. You have to make a choice and say, okay, the current is going to go this way for this one. The charge is going to be positive on the top, or it's going to be negative on the top. It doesn't actually matter which way you define it, as long as you're consistent with the way that you define it and the way that you go through your loop calculations. So then the next thing that you can do is you can draw some surfaces for junctions. After that, draw your loops, and then once you have those things all labeled, then you can write the equations that you need in order to solve them. Now, I did say there's a warning in the notes that you need to make sure that you go through all those steps, otherwise we just won't grade the problems that you're solving. That might seem excessively harsh, but the reason why we do it like that is there's too many ways to get different negative signs, and it becomes impossible for us to check for consistency if you don't label something. Yeah?
How are the charges and the currents related to each other when you're labeling the circuit?
I'll get to that. And then ultimately, with time-independent circuits, they're not related to each other. Because you can say that current is charged with time, right, dimensionally. But when we're talking about time-independent circuits, the charge is going to be constant on the plates. There's not going to be charge moving to it. Later in the semester, when we get to time-dependent circuits, what we can say is that the current is related to the charge via I is equal to dq dt. But we won't do that here, and you'll see why, what exactly the difference is when we're going through the examples. Okay. Other questions before I do this example? Okay. So in the notes I had this circuit example where I had some battery here, some resistor, another resistor, a third resistor, and a capacitor, where this was some V, this is R1, this is R2, this is R3, and this is C. Okay. So going through our rules here, now I chose it in a particular way when I did it in the notes, but I'm actually going to do it differently. I wanted you guys to do it differently as well so you can see that it gives you the same thing ultimately. So the first thing I'm going to do is I'm going to label the charges on the capacitor. So this is going to be some minus Q, some plus Q. Like I said, I could choose this to be either way. In the notes, I chose this to be a plus Q. Now let's label the current. So I'm going to say that there's some current I, let's call this I2 because this is the R2. This is some current I1, and then this is some current I3. Okay. Now, to draw the box that we're finding the flux of the current density through is going to be just to draw some box around this. And so what this equation tells us is that whatever current is going in is going to be equal to the current going out. And so this says that from the integral of j dot ds is equal to 0, this implies that I1 plus I2 is equal to I3. Okay, so that's the first thing that I can do is do that. Now the next thing I can do is to draw some loops, and I'm just going to draw this loop and this loop. Like I said, you make any choice you want. Now ultimately what I'm going to need here, I'm going to need 3 equations because I have 3 unknowns ultimately, and I'll explain why that is. But let's just call this some loop. Let's not call it a capital I. Let's call this a 1 and call this a 2. Okay. So for our loop 1, the way that we're going to do this is we pick somewhere on here to start. And so what this says really is the integral of E dot dl around loop 1 is equal to 0, right? That's just applying the definition. But now what we want to do is we want to say, well, what are the contributions to this integral over the closed loop in terms of the things that we have here? So let's start here, okay? And then we're going to go around the loop. So the first thing that I'm going to see when I get there, when I get here is this resistor R2. It has some current I2 going through it, and so this is going to be the integral over R2 of E dot dl, which is going to be equal to, now this one has some current going in the same direction as the direction of the loop, right? Because the loop's going around like this, my current's going this way, and so this says that this is going to be some plus I2 R2. And the reason, yeah?
When you're choosing the direction of the current, does it really matter, like in the loop?
Nope, it doesn't matter. It doesn't matter. And
the loop going...
Yeah, I could have said the loop goes this way, I could have said the loop goes that way, I could say this current goes up, I could say this current goes down.
Depending on what the battery's doing, right?
In reality, what happens, it does.
Okay.
In reality, what we'll find one of my Q's is going to be negative when I solve this in the end, but that just means it's reversed from the way I labeled it.
Okay, so that's the battery.
Right. So there is actually the direction the current goes, but we kind of put that in a black box and say, well, imagine I don't know what that is, but let me solve this system as if it actually went this way and that way. And then what we end up finding in the end is when we do that, and you'll see here, for this particular example, I'm going to find that I2 is negative when I solve it, which just means that I2 is actually the opposite direction as the way I drew it.
Okay. So the direction that you're putting your I's and your R's down there is dependent on it. If it's going with or going against.
Exactly. That's how I got this plus sign. So this loop is going around this way, the current goes this way, this gives me a plus sign. And this is the real difference between the convention that I use and the Kirchhoff convention. Kirchhoff would say this is negative. And it basically multiplies what I have by a negative sign. So it ends up being the same equation, but for one, I think it's a little bit easier to think about it like this, to say if I go around the loop this way, the current's this way, then this is plus. Kirchhoff says that that's minus, but I don't want to get into it too much, but there's more of a reason why I'm doing it like this. And that's going to come later when we do Faraday's law. Okay, so now, and you'll see the counterexample here when I get to this one. So now I want to find the integral over R1, because I'm coming around this loop. I get to here now. So this is E dot dl for R1. This one has the current going the opposite direction as the direction of the loop. And so this one is going to be minus I1 R1. And ultimately, the reason for these signs comes down to the dot product. Because the electric field is going to be the same direction as the current, right? Because E is equal to rho J, right? Because E is equal to rho J, whatever direction the current's pointing is the direction the electric field is pointing. And the direction of the loop is the direction that I have here, which is the same as the direction as dl. So when these things go in opposite directions, this dot product gives me a negative sign. When they go in the same direction, the dot product gives me a positive sign. Again, this is why I prefer this method. Okay, so now the last piece that we need to complete this whole loop is to do the integral over the battery of E dot dl. And this one is going to say that this is going to be the positive side of the battery, this is the negative side of the battery. We know that the electric field points from positive to negative, so the electric field points this way. And so we know then that when I get to this battery and I integrate across it, the dl is the same direction as the E, and so this says that this is a plus phi. Okay. Now, again, ways that this can be simple when you look at this and say, okay, I go around the loop. If I see the positive side of a battery, I get positive V. If I went around the loop the other way, I would see the negative side. That means that this would be a negative V. So now the last thing I need to do is just to put these together to find my equation here, and that's just to say that the sum of all these is equal to 0, and so V plus I2 R2 minus I1 R1 is equal to 0. Okay? So that's one equation. Okay, and I have another equation. Ultimately, we're going to need, well, we really need 4 equations. We need 4 equations because we have 4 unknowns. The next equation is going to come from doing the loop here, okay? So when I do this loop, this is the integral over the closed loop for loop 2 of E dot dl, which is going to be equal to 0, and so I can break this apart again into the individual pieces, and so this is going to be the integral over R1 of E dot dl, which is going to be equal to plus I2 R2. Is there a question? No? Okay. Then I get to this portion right here. So this is going to be the integral of over R3 of E dot dl. This one is going to have the current I3 going in the same direction as R3, or as the loop through R3, and so this is going to be plus I3, R3. And then the last piece that we get to is the capacitor. And so when I go across the capacitor, I say that this is going to be equal to the, this is the integral over C of E dot dl. This goes from negative to positive. I hit a negative side first. And so this says that this is going to be minus Q divided by C. Okay? Everybody with me? Okay. So now the last thing I need to do is to put all of this together. And then that's going to say that I2 R2 plus I3 R3 is equal to, minus Q over C is equal to 0. That's the next equation. So I have 3 equations. Yeah?
Since you already did R2 and I2 in the first one, do you really need to do it in the second one?
Yes.
Positive?
Yes, and it's important because these are 2 separate loops, right? This is this loop and this is this loop, right? But both of those loops contain this piece. So in order to go around the closed loop for loop 1, I go here, I go across here, I go here, I go here, right? For the second loop, I go like this. But for both of them, I'm still going across the I2, R2. And so really, when I say the integral over the closed loop, it really means sum all pieces that I go across. And then that's equal to 0. Okay, and because for both loops I actually go across I2, then I need to include that. But there's a third loop that I could have drawn. I could have drawn the loop that goes around the outside. That one doesn't have I2. That one just goes like this. Okay? All right. So we have 3 equations, 4 unknowns. There's one more equation that we need. And it actually ultimately gets to the question that he was asking before over here about the relationship between the charge and the current. And in the steady state, this charge on this capacitor is constant. And because that charge on the capacitor is constant, there can't be any current flowing to it or from it. So anything that's in the line that this capacitor is in has no current flowing through it. And what that says actually is that I3 is equal to 0. Okay? Does everybody follow that argument? It's important for time independent circuits that any portion of a circuit that has a capacitor in it, the capacitor will be fully charged and there's not going to be any current flowing to it. Yeah?
How do you know when a capacitor is fully charged?
You say that after a long time. So, and then also assuming that batteries last forever. But when I say after a long time, say there was a switch here. Initially, there's no charge in the capacitor, then I close the switch. What's going to happen is current's going to flow around this circuit until the capacitor reaches the maximum amount of charge that it can hold. And then once it reaches that maximum amount, there's not going to be any more going to it and there's not going to be any leaving it. So that means that this is fully charged. Okay, so that'll be like a qualifier that's written in questions after a very long time. That's really what that means. After a really long time means you close the switch, you put all the charge that you can in the capacitor, and then there's no current flowing to or from it. Yeah.
So if we have that qualifier in there that says
afterwards, yeah.
Oh, sorry. So we have a current going to or from there for a long time. Is that current always going to be 0?
In the long time case, but this is ultimately the difference between the time dependent and the time independent circuit. And for this exam, we're only going to be doing time independent circuits. Later, we're going to be doing time dependent circuits, and then ultimately, what you're going to have to say is there's some relationship between the charge that's on the capacitor and the current that flows to or from it, such that the current is going to be related to the time derivative of the charge. And this will give you some differential equation that you have to solve, but we're not there yet. That'll be actually after we do magnetism. So that'll be one of the last things that we do. But for this exam and these problems in particular, we're always going to say that capacitors are fully charged and there's no current flowing to or from them. Okay. Yeah, you had a question too.
So when the capacitor is fully charged, does it just act like an open switch then? Basically.
In a way, yeah, in a way. It's almost like you broke this part.
Yeah.
So there's not current flowing to it from it. You could think about it like that if you want. Yeah. Okay. Other questions? Yeah.
In general, how do you know how many flows that you need for your equation?
Sure. That's not a question that's easy for me to answer. It's something that the more problems you'll do, you'll get accustomed to realizing how many you need. So I guess what you're asking here is like, I could have also labeled some I5 and I6, right? I could have done another junction. Well, really, I1 and I6 are the same, and I3 and I5 are the same, because it's all part of the same portion of wire before a junction. So there could be more, but then that just means that you have more unknowns, more equations, and so if I wanted to include these as well, in order to fully parameterize the system, what I would say is the additional equations that I need would say that I1 is equal to I6, and I3 is equal to I5. You could do that, but I guess, yeah, I don't know that I have like the answer to the question that you're asking, because I think what you're trying to ask is there a systematic way that I can say, if I look at this circuit, I know I need exactly this number of equations. It's something you just have to identify on the fly. I couldn't tell you I couldn't even really tell you my own personal rationale for why I would say there were n number of equations here because there are n number of unknowns. It's something that I would look at and identify.
What about more so is like, you could have done like 3 equations at the beginning, like based on the different like directions of flow you could have done, right? And you chose 2 of them. Why did you choose to do 2 instead of 3?
Oh, okay, so why did I do these 2 loops and not all 3 loops?
Yeah.
Because I used a junction here. So ultimately what I was getting at here was you need 3 equations and 3 unknowns. You could build those 3 equations by saying, I'm going to just do 3 loops and not care about the junction. Typically, as far as the algebra goes, it's easier if one of the equations that you have is a junction. It simplifies things. In particular, this case ends up saying that I2 is equal to minus I1. That makes this a lot easier to solve than the third equation that I would get from doing the loop around the outside. But yeah, however you want to find your 3 equations is perfectly fine. But I would say, generally speaking, it's easier to use a junction than it is to do a third loop. Okay? Other questions? Okay, so really the only thing left to do here, and I don't want to take up too much more time doing this, would be to solve this system of equations. So I have this equation, I have this equation, and after I said that I3 is equal to 0, I'd say that I1 is equal to minus I2, and that's the last equation. So actually, that's not too bad. So this here says that if I plug this in here and then solve for I1, this is going to say that I1 is going to be equal to V divided by R1 plus R2. And then I can take that and I can plug it into this equation. This is 0 to solve for Q. Okay? Any questions about this? Yeah.
So what are the unknowns in this problem?
The unknowns here are, I mean, there's actually more, because I said there's 4 equations, 4 unknowns. I would say the unknowns were I1, I2, I3, and Q. R1, R2, R3, C, and V are all known. But I mean, it's possible that I could give you a problem where I say, well, I know I here, and instead I'm not going to tell you what V is. But here it's just the 4 unknowns, and I was able to get rid of this one very quickly by saying there's no current flowing through here. So it reduces nicely to 3 equations, 3 unknowns, which is why I had this equation, and that equation. Okay? Yeah.
I was late, so you might have covered this already. how is there a way that you can always know where to put the sign on which Q, or is that not another thing that you kind of guess about?
So how do I know if I make this minus Q or plus Q? You guess. But and the thing is, you want to be consistent. You want to be consistent with the way that you're defining it and the way that you're doing the loop equations. Now, for this one, it's actually easy to know what it should be. This should be plus Q, and this should be minus Q, because this is the positive terminal. This is the negative terminal. Not all problems are going to be easy to determine which way the Q should be, because I could have also put another battery here. So I could put another battery here, but then it's going to be plus Q or minus Q depending on what the ratio of these two V's are. So you wouldn't necessarily know which side is which in terms of whether the charge is positive or negative, but you just define it, and then you carry through the calculation. It's kind of similar to, you guys remember in mechanics doing problems like this. So I have some mass hanging, some mass on an inclined plane hanging over a pulley, and it could go either direction, right? Depending on what the ratio of the masses are and what the angle is. But you can solve this problem just by making a choice and saying, I'm going to assume that it goes this way. And then set up the equations exactly like that. And then if you end up finding that the ratio of these masses and what the angle is such that it actually moves the other way, then the acceleration that you solved for here would just be negative. But as long as you're consistent with your definitions and you're going through the physics of it properly, it'll give you the right answer regardless. Okay. Other questions? Yeah.
One more. When you had negative I2, and just thinking about it, like the current flowing.
Yeah.
Yeah. So would you? Is that like a coordinate system thing, or
it's really just what, and it makes sense that this should be negative this if this is 0, right? Mm-hmm. Because that just means that the current should flow around like this, and there's no current over here. And in a sense, it is kind of like a coordinate thing in a way, I think, is what you're trying to say. That I made a choice for the direction this points.
The absolute value of the charge would be, the same. Because it's
right.
There's no current flowing over here, so all the current has to. So that's, I guess what I'm asking is if all the current that is flowing through R1 and then through R2. Why do you say that the current's negative in one place and
It's because of the definition that I have here. So I define this current to go this way. I1 goes this way, I2 goes this way. But that's not the direction I2 goes. It actually goes the direction you think it will. And that's why it's negative here relative to the way that I defined it. So it is the direction you think it should, and that negative sign takes care of it.
So you really can draw the directions of current willy-nilly at the beginning and
Yep. And then you just have to make sure that you're consistent with your loops. Okay? Any other questions? Okay. So like I said, we're just going to be doing, these are really things that you just have to practice and use the rules yourself to get familiar with. But the problems we'll do in class today, I think I was a little ambitious to give you 3. But this is the first one. This is the first one. So just go through the rules and we'll see where we are at the end. I might reduce the homework if we don't finish all this. I don't want to give you 6 over the weekend if that's too much. Yeah. I'll come help you in a second. Oh, sorry.